Welcome back. In our first lecture, we explored the evolution of database systems and got a high-level overview of the different types of databases available today. Now we are ready to focus specifically on relational databases, which will be our primary focus throughout this course. By the end of this session, you understand not just what relational databases are, but why they've remained so dominant for over 50 years, and how their core concepts translate into practical database design. We'll start with the history of relational databases in SQL, explore why they remain relevant today, dive into core concepts with visual explanations, compare database tables to spreadsheets, and finish with an introduction to ACID properties and transactions. Let's begin with how it all started. The story of relational databases begins in the late 1960s, during a time when data management was becoming increasingly complex. Before relational databases, as we saw in the last lesson, organizations primarily use hierarchical and network database models, which store data in rigid tree-like or graph structures. These early systems worked, but they had significant limitations. Data relationships were hard-coded into physical storage structure, making changes difficult. Retrieving data required navigating through these predefined paths, which meant application developers needed intimate knowledge of the database structure. The earliest computerized data management systems were simple file systems. Organizations stored data in flat files with fixed formats, which quickly became unwieldy as data volumes grew. Searching through these files was inefficient, and maintaining data consistency across multiple files was nearly impossible. Imagine trying to manage a company's entire inventory using nothing but text files. If a product appears in multiple files, updating it would require finding and changing every instance, a recipe for inconsistency and errors. The first major advancement came with hierarchical databases in the mid-1960s. IBM's Information Management System, or IMS, developed for NASA's Apollo program, organized data in tree-like structures, where each record had a single parent. While more sophisticated than flat files, these systems struggle with many-to-many relationships like we discussed before and require complex programming to navigate. Think of a hierarchical database like a family tree, where each person can have only one parent. This works fine for some relationships, but breaks down when modeling something like a university where a student can take multiple courses and each course can have multiple students. Network databases followed in the late 1960s, with systems like Integrated Data Store, IDS. This improved the hierarchical model by allowing records to have multiple parent-child relationships, creating a more flexible network structure. However, application developers still needed to navigate these complex structures manually, following predefined paths through the data. Using the university database as an example, if courses are below the tree's root node, there is no shortcut to students or professors bypassing courses. Edgar F. Ford, a mathematician who turned a computer scientist, began his career at IBM in 1949 as a programming mathematician. After serving the Royal Air Force, briefly working in Canada, he returned to IBM in 1957, where he would later revolutionize data management. The true revolution came in 1970 when Ford published his groundbreaking paper, A Relational Model of Data for Large Shared Data Banks. Ford proposed a radically different approach, organizing data in tables, relations, with rows and columns, where relationships between data will be represented by values rather than physical structures. Even though this sounds very simple nowadays, it was a paradigm shift. Instead of forcing data into hierarchical structures, Ford's model allowed data to be represented in a way that was much closer to how we naturally think about information. Ford's model was based on mathematical set theory and predicate logic. He defined a relation as a set of tuples, rows, where each tuple contained a set of attributes, values, or columns. The key innovation was the relationship between data would be established by matching values in different tables, not by physical pointers or predefined paths. This approach offered tremendous flexibility. Database structures could be changed without rewriting the applications, and users could ask questions about the data without needing to know how it was physically stored. Ford's paper outlined several rules that a database system should follow to be considered truly relational. These rules emphasize the separation of logical data representation from physical storage details, and the ability to manipulate data using a high-level language rather than navigation commands. Following theoretical work, IBM researchers Donald Chamberlain and Raymond Boyce, I hope I'm pronouncing their name correctly, developed a structured English query language, or SQL, in the early 1970s as a practical implementation of Code's ideas. This language was later renamed to SQL as you know today, which stands for Structured Query Language. It was for trademark reasons, actually, but until today, many people still pronounce it SQL, right? SQL, or SQL, was designed to be accessible, closer to natural English than to traditional programming languages. This made database queries more intuitive and opened database access to a wider range of users. IBM's System R project, started in 1974, was the first implementation of SQL in relational database concepts. It introduced many features we now take for granted, including the basic SQL commands like select, insert, update, delete. Don't worry, we're going to cover all of them in individual lectures. It also introduced transaction management and query optimization. While IBM was developing System R, other researchers were also exploring relational database technology. At the University of California, Berkeley, Michael Stonebreaker and Eugene Wong, again, I hope I pronounced their name correctly, began working on INGRES, Interactive Graphics and Retrieval System. In 1973, another pioneering relational database system. The first commercial SQL-based relational database management system was, guess what? Oracle. Released in 1979 by Relational Software Incorporation, later renamed Oracle Corporation. Oracle beat IBM to market, though IBM released its own commercial product, SQL-DS, in 1981, followed by DB2 in 1983. As SQL implementations went all over the place, in the early 1980s, the need for standardization became apparent. In 1986, the American National Standards Institute, or ANSI, published the first official SQL standard, known as SQL 86 or SQL 1. This version introduced fundamental DDL and DML operation, which stands for Data Definition Language and Data Manipulation Language. We're going to cover them in separate lessons. This initial standard formalized basic query operations and table management. Standardization was crucial for the adoption of relational technology. It means that skills and applications could be more easily transferred between different database systems, reducing vendor lock-in. The International Organization for Standardization, or ISO, adopted the ANSI standard in 1987. Since then, the SQL standard has been regularly updated with major revisions. 1989 with SQL 89, 1992, 1999 which was SQL 3, 2003, 2006 and so on. We don't need to go version by version explaining what they standardized. However, the version SQL 92, also known as SQL 2, represented a transformative milestone in database technology, marking the most comprehensive overhaul of the SQL standard since its inception. In terms of advanced query capabilities, SQL 92 revolutionized data retrieval by introducing sophisticated join operations, including inner join, left outer join, right outer join, and full outer join. Don't worry, we're going to cover them all in separate lessons. These joins enable complex data relationships and analysis that weren't previously possible in standardized SQL. In terms of data type expansion, the standard introduced crucial new data types like date, time, timestamp, interval for time calculations, bit string for binary data, and varchar for strings. When it comes to data integrity, SQL 92 strengthened database reliability through transaction isolation levels, enhanced constraint mechanisms like check, unique, and foreign keys, and declarative referential integrity. In terms of schema management, the standard introduced powerful schema modification capabilities. There we can say alter and drop commands, temporary tables, information schema for metadata management, and so on. The impact on the industry was huge. The SQL 92 standard's comprehensive feature set transformed it from a simple query language into a robust database management standard. Major database systems, including Oracle, DB2, and SQL Server, adopt these features, significantly improving database interoperability. Each following revision of the standard has added new features, from basic elements like jobs and transactions to advanced capabilities like object relational features, XML support, and window functions. This one we're going to cover in a separate lecture. However, no database management system implements the entire standard, and most add proprietary extensions. The 1980s saw the explosive growth in relational database adoption. By the mid of 1980s, relational systems had largely displaced earlier hierarchical network databases for new applications. The client-server computing model, which became dominant in the late 1980s and early 1990s, was a perfect fit for relational databases, with the BMS running a central server accessed by multiple client applications. The rise of personal computers and local area networks made relational database accessible to small organizations, not just large enterprises with mainframes. The 1990s brought increased competition among relational database vendors, with products like Microsoft SQL Server, Sybase, Informatics, and others challenging Oracle and IBM. This decade also saw the rise of open-source relational databases, with MySQL, created in 1995, and PostgreSQL, which evolved from Postgres project started in the mid-1980s. PostgreSQL, of course, has a particularly interesting story, but we're going to cover this in the next lesson. The early 2000s saw relational databases adapt to web applications and e-commerce, with improvements in scalability, performance, and support for web technologies. Features like store procedures, triggers, and better transaction management became standard. And this brings us to where we are today, in a world where relational databases continue to power most critical business applications despite the rise of alternative approaches. And that leads perfectly into our next topic: why relational databases still matter in today's diverse database landscape. Despite the rise of NoSQL database over the past decade, relational databases remain the backbone of most enterprise applications and data systems. This continued dominance is a testament to the fundamental strengths of the relational model. You might be wondering why, with all the hype around NoSQL technologies, we are still focusing on a relational database like PostgreSQL. The answer lies in understanding both enduring strengths of relational databases and how they've evolved to meet modern challenges. While NoSQL databases emerged to address specific limitations of traditional relational systems, particularly around scalability and schema flexibility, relational databases have continued to evolve and adapt. Consider what happens when data integrity is compromised in banking applications, or when inconsistent data appears in a healthcare system. The consequence can be severe. This is why many organizations still choose relational database for their mission-critical systems. It's important to highlight, though, that relational databases are not the only option when it comes to consistency and are not always consistent. As we'll cover in section 4, totally dedicated for data modeling, consistency is just what's commonly desired and achieved with relational models. And all normalization forms that you're gonna learn are basically when we trade off disk space, availability, and sometimes even performance to make sure our data is always consistent. Remember, consistency is key to relational databases. Today's enterprise landscape shows relational database powering everything from traditional transaction processing systems to modern web applications. Financial institutions, healthcare providers, government agencies, and retail businesses all rely heavily on relational database for their core operations. Let's look at some specific use cases where relational databases continue to excel. Relational databases are particularly well suited for transaction processing systems where data integrity is paramount, applications with complex querying requirements, systems with well-defined stable data structures, scenarios requiring strong consistency guarantees, applications where data relationships are complex and important. Many modern web applications use a combination of technologies, perhaps a relational database for transactional data and user information, alongside NoSQL solutions for specific features like caching or storing structured content. Within the relational database world, PostgreSQL has emerged as a leading choice, particularly for organizations looking for an open-source alternative to commercial databases. PostgreSQL is often described as the world's most advanced open-source relational database, combining robust enterprise features with the flexibility and cost advantages of open-source software. What makes PostgreSQL particularly interesting is how it has evolved beyond the traditional boundaries of relational database while maintaining its core strengths. It has gained significant market share in recent years, with adoption across startups, enterprise, and government organizations. Its reputation for reliability, data integrity, and standards compliance makes it suitable for mission-critical applications. Of course, we'll explore PostgreSQL specific features and capabilities in much more details in Lecture 3, but for now, let's focus on how it bridges the relational and non-relational worlds. One of the most interesting developments in the database world is the convergence of relational and non-relational features. PostgreSQL has been at the forefront of this trend, incorporating many NoSQL-like capabilities while maintaining its relational foundation. These hybrid approaches gives developers the best of both worlds: the reliability of consistency in relational systems with the flexibility and specialized capabilities previously only found in NoSQL database. For example, PostgreSQL now supports JSON and JSONB data types, allowing for schemaless document storage within a relational context. It offers array types, HStore for key value store, and full text search capabilities. With extensions like PostGIS, it can even function as a spatial database. This means you can store and query structured relational data alongside semi-structured or unstructured data in the same database, using the same transaction mechanisms and security model. Many traditional relational database systems have incorporated some NoSQL features, while some NoSQL systems have added more relational capabilities like secondary indexes and join operations. The line between these two categories continues to blur as database systems evolve and meet diverse application needs. So now that we understand why relational databases remain relevant and how they've evolved to meet modern challenges, let's dive deeper into the core concepts that make them work. At the heart of relational model are relations, which we typically call tables in practical database world. A relation is formally defined as a set of tuples that have the same attributes. In simple terms, a table is a collection of rows with the same columns. Imagine we are building a database for a healthcare center. Here's what a patient's relation might look like. Each horizontal row in this table is a tuple, a single record representing one patient. The entire table is a relation, containing all the patients in our database. What's important to understand is that unlike a spreadsheet, the order of rows in a relation doesn't really matter. In relational theory, a relation is a set of tuples, and sets don't have any inherent ordering. When we want data in a specific order, we explicitly request it using a clause in our query. Another key difference from spreadsheets is that all values in a tuple must be atomic, meaning they can't be further divided into meaningful components within the relational model. This is part of what's called first normal form, which we'll explore more when we discuss normalizations. Each column in a relation represents an attribute, a property or characteristic of the entity we are modeling. In our healthcare example, the first is patient ID, first name, last name, date of birth, and insurance ID. Think of attributes as questions we can ask about each entity. What's the patient's insurance ID? When was he or she born? Each attribute has a domain, the set of allowable values for that attribute. The domain defines the data type, which could be integer, text, date, etc. Any constraints on values, like it can only be positive, must be within a certain range, whether new values are permitted or not. In PostgreSQL, domains are implemented through data types and constraints. For example, in a bookstore, we might define the price attribute in a books table as a decimal type with a check constraint ensuring it's greater than 0. Makes sense, right? Domains help ensure data integrity by preventing invalid data from entering the database. For instance, in the same books table, if we define the publication year as an integer between 1450, the invention of the printing press, and the current year, the database would reject any attempt to insert a book with a publication year of 3025 or 1200, for example. Keys are crucial for establishing relationships between tables and ensuring data integrity. There are several types of keys in relational databases. Now let's explore each type of key and understand why they are essential for a well-designed database. A primary key is an attribute or combination of attributes that uniquely identifies each tuple in a relation. In our books example, book ID serves as the primary key. No two books can have the same ID. Primary keys must be unique and cannot contain no values. Primary keys act as the identity card for each row. When we need to refer the specific book, we use its primary key rather than something potentially ambiguous like its title. A candidate key is any attribute or combination of attributes that could potentially serve as a primary key because it uniquely identifies tuples. A relation might have multiple candidate keys, but we designate one as the primary key. For instance, if every book had a unique ISBN number, both book ID and ISBN would be candidate keys, but we typically choose one, probably book ID, as the primary key. A foreign key is an attribute or set of attributes in one relation that refers to a primary key of another relation. Foreign keys establish relationships between tables. In our example, author ID in the books table would be a foreign key referencing the primary key of the authors table. This is how we connect related data across tables. Instead of repeating all the author information in every book record, we just include a reference to the author's unique identifier. A database schema is the structure that defines how data is organized in a database. It includes tables, their attributes, relationships, constraints, and other database objects. Don't worry, we're going to cover them all in much more details. Visualizing the schema helps us understand the relationships between different entities in our database. Let's expand our bookstore example to include authors and customer orders. Here's a lossy summary representation of our bookstore database schema. We have first books table with book ID, title, author ID, which is a foreign key pointing to author's table, publication year, and price. Second, we have the authors table with author ID, which is a primary key, name, birth year, and nationality. Next, we have orders table with order ID and customer ID. Order ID is the primary key, and the customer ID is a foreign key pointing to customers in order date. Next, we have order items, which is a relationship between ordered and books. The order ID is a foreign key to ordered, and book ID is a foreign key to books. It has also quantity and price at time of order. We use a copy of the price just to make sure we know the price when it was ordered, in case that the product changed the price later on. Next, we have customers table, customer ID, name, email, and address. The arrows in this diagram indicate the relationship between tables through foreign keys. For example, author ID in books table points to the author ID in the authors table, establishing a relationship between books and their authors. Data dictionary. Old school people or companies that require formal documentations can also represent the same data model using a big table called data dictionaries, where they basically go table by table, field by field, expliciting their name, domains, and a description of what they cater for. Here is a data dictionary table that fully documents each database table and its attributes in our bookstore. We're not gonna go over everything in this table, but I think you got the point. Thankfully, we now live in a world where generative AI can either create a data dictionary from database DDL, a bunch of create tables, or vice versa. Finally, visual representations are usually handy. We are going to cover visual modeling in details in Section 4, Database Modeling, when we discuss modeling types, conceptual, logical, and physical, as well as different notation. Normalization is a systematic process of organizing database tables to minimize data redundancy and improve data integrity. It involves dividing large tables into smaller, related tables and defining relationships between them. Notice that our bookstore schema has multiple tables rather than just one giant table containing all information. This is a result of normalization. So we can say the main normalization goals are eliminating redundant data, storing the same data in multiple places, ensuring data dependencies make sense. Data is stored in logical locations, facilitating data maintenance, and reducing anomalies. We'll explore normalization in depth in Section 4, where we'll cover the various normal forms and how to apply them in practical database design. For now, just understand that normalization is about organizing data efficiently and logically. Many people familiar with spreadsheet applications like Microsoft Excel or Google Sheets often wonder how database tables differ from the spreadsheets they already know. While both organize data in rows and columns, the similarities ain't just there. Understanding these differences is crucial because it helps explain why businesses move from spreadsheets to database as the data needs grow more complex. Let's examine the key distinctions between these two approaches to data management. Database tables have a rigid predefined structure where each column has a specific data type and constraints. Every row in a table must conform to the defined structure, with each column accepting only values of the specified type. In spreadsheets, a single cell can contain virtually anything: text, numbers, formulas, and even images. Columns don't have enforced types, meaning you could have numbers, dates, and text all mixed in the same column. Spreadsheets also allow merged cells, formatting for visual emphasis, and embedded charts, features that don't exist in database tables. Think about a company's inventory system. In a spreadsheet, someone might color-code rows for low stock items, or use bold text for important products. In a database table, this information will be represented by actual data fields, like stock level or priority flag, that can be queried and processed programmatically. Databases provide robust mechanisms to ensure data integrity that simply don't exist in spreadsheet. These include primary keys that guarantee each row is uniquely identifiable, foreign keys that maintain relationships between tables, check constraints that validate data against business rules, not null constraints that prevent missing values, unique constraints that prevent duplicate values, triggers that automate validations and updates. All of these mechanisms are enforced by the database system itself, not by application logic or user diligence. In PostgreSQL specifically, you can define constraints when creating a table, but we are going to cover these in next lessons. Database query capabilities far exceed what's possible in spreadsheets. SQL provides a powerful, standardized language for data retrieval and manipulation. Complex operations like joins across multiple tables, aggregations, and subqueries allow for sophisticated data analysis that would be extremely difficult in spreadsheets. While spreadsheets do offer functions and formulas, they are limited compared to the expressive power of SQL. Consider a scenario where you need to find all customers who place orders totaling more than $1,000 in the last month, grouped by their region. In SQL, this might be just one command statement like that. First, we select what we want from a table or a join of tables that contain all the necessary information. Then we filter out rows that don't meet the defined criteria and squash all records into aggregated ones, grouping them by what we need. And again, filter out aggregation records that don't meet what we want. Finally, we define the order we want to see the results in. I know I didn't explain what this particular query is doing, but I did that on purpose because I want to challenge you. If this query doesn't make any sense to you, take a note, write it down, or screenshot, then come back to it after you finish section 3 of this course. I bet this will be crystal clear before your eyes, and you think, really? Was that the query that didn't make sense to me before? Now you're thinking accomplishing this in a spreadsheet. This would require complex formulas, likely spanning several worksheets and pivot tables. And the most important thing, it will become unwieldy as your data volume grows. Now that we have explored the structure and relationships between relational database, let's turn our attention to one of the most powerful features: transactions. Transactions are logical units of work that either complete entirely or not at all, and they are governed by what we call ACID properties. The first letter of ACID, atomicity, is when a transaction is all or nothing. In other words, it's treated as a single, indivisible unit of work. Either all operations within the transaction are completed successfully or none of them reply to the database. I'm going to skip the overused bank transfer example that everyone reaches for to explain atomic transactions and consider something different: an e-commerce order system. Imagine a customer placing an order in our bookstore. This transaction might involve checking that the books are in stock, reducing the inventory count for each book, creating a new order, adding items to the order, calculating the total price with tax, recording the customer's payment information. With atomicity, if any of these steps fails, perhaps a book is suddenly out of stock or payment processing fails, the entire transaction is rolled back. The inventory counts remain unchanged, no order is created, and the database returns to its previous consistent state. Just an important disclaimer here. This example doesn't consider the complexity of external payments with third-party integrations. So just imagine we can handle this within our system, not making external calls. Atomicity is crucial for business integrity. Without atomicity, you might end up with reduced inventory but no corresponding order, or an order with no payment records, scenarios that create both technical and business problems. Consistency guarantees that a transaction can only bring database from a valid state to another valid state, maintaining all predefined rules, constraints, and triggers. Think of consistency as the guardian of your database business rules and logical integrity. In PostgreSQL, consistency is enforced through various mechanisms. Let's have a look at them. Number 1, data type constraints ensure values match their defined types. 2, not null constraints prevent missing required data. 3, check constraints enforce business rules. 4, unique constraints prevent duplicate values. 5, foreign constraints maintain relationships between tables. And 6, triggers can enforce complex business logic. Back to our bookstore example, consistency is represented by no order can be created from non-existent books. Book prices cannot be negative. Customer IDs in orders must match existing customers. Order dates can be in the future. By the way, consistency works hand in hand with atomicity. If any constraint is violated during a transaction, the entire transaction is rolled back, preserving both databases' consistent state and transaction atomicity. Isolation addresses what happens when multiple transactions are executed concurrently. It determines how and when changes made by one transaction become visible to others. This is particularly important in modern applications where hundreds or thousands of users might be interacting with the database simultaneously. PostgreSQL offers 4 standard isolation levels, each with different trade-offs between performance and consistency. Here's the list from the least to the most isolated level. 1. Read uncommitted. 2. Read committed. 3. Repeatable read. 4. Serializable. The default isolation level is read committed, but you can adjust based on your specific needs. Read committed only shows committed changes from other transactions and provides a good balance between performance and consistency for most applications. In the strongest isolation level, serializable, as its name suggests, transactions can run fully sequentially, which can cause severe performance degradations in highly concurrent systems, but brings the highest protection level against different concurrency phenomena. It's a bit too early to go down into this rabbit hole. We'll discuss this in detail in our transaction lesson in section 5. For now, let's go ahead and cover the last letter of ACID. Durability guarantees that once a transaction has been committed, it remains committed even in the case of system failure, such as power outages and crashes. This is what allows you to sleep at night knowing that your data won't simply vanish if something goes wrong with the server. PostgreSQL implements durability through several mechanisms. The first and most prominent one is write-ahead logging, or WAL. Changes are first recorded in a log before being applied to the database files. Second, checkpoints. Regular checkpoints where modified data is guaranteed to be written to disks. FC calls, file systems calls to ensure data is physically written to disk, not just cached. Transaction commit acknowledgement only confirms commit after durability is guaranteed. These mechanisms work together to make committed transactions survive even catastrophic failures. When the system recovers, it uses WAL files to restore any committed transaction that might not have been fully written to the actual database files. The trade-off here is between performance and durability. More aggressive durability settings provide stronger guarantees but can impact write performance. PostgreSQL allows you to configure these settings based on your specific requirements. We'll explore transactions in much greater depth in dedicated lecture on transaction management and ACID properties later in our advanced SQL section. There, we'll dive into isolation levels, lock-in mechanisms, and advanced transaction patterns. For now, understand that transactions are one of the most powerful features of relational databases like PostgreSQL. They are what allow these databases to maintain data integrity in complex, multi-user environments with concurrent operations. This concludes our deep dive into relational database. In our next lecture, we'll focus specifically on PostgreSQL, exploring its unique features, architecture, and advantages compared to other database systems.